some mathematical definition. Okay, so we will say sigma I, that is a strategy player I can choose, is best response to sigma minus I, that's strategies chosen by other players. So we say sigma I is best response to sigma minus I if and only if this inequality is true. So on the left-hand side, you have expected payoff when player I chooses sigma I, while the other guy chooses sigma minus I. On the right-hand side, you have payoff when player I chooses sigma I prime instead of sigma I. And this payoff has to be smaller than the original payoff for any possible sigma I prime. Okay, so in that sense, if that's the case, we will say that sigma I is best response to sigma minus I. Okay, the reason we call this best response is kind of obvious, right? Player I can maximize his or her payoff against sigma minus I by choosing sigma I. Okay, if player I deviates from sigma I to any other possible strategies, sigma I prime, the payoff never becomes larger. Okay? So sigma I is best strategy in that sense, as long as the other guys play sigma minus I. Okay, so then for each I, player I, so remember that N is the set of players. So each I and each sigma minus I, we will define BR for best response, subscript I for player I, to sigma minus I. So that's the set of all player I's strategies, which is a best response to sigma minus I. Okay. So using conventional notation, you can actually check this is BRI minus sigma minus I. That is exactly equal to argmax UI sigma I sigma minus I. So what is that? So what is that argmax? So this is a maximization problem, right? So you fixed sigma minus I. So sigma minus I is fixed. And then you are asking what is the best choice of sigma I, right? And to answer the question, you have to answer this maximization problem, right? Then after you solve this maximization problem, you have some solution. Sometimes we have multiple solutions, right? So maximization problems sometimes, can have more than one solution. Okay? Then and keeping that in your mind, if you put R here in front of everything, so that is simply the set of optimal solution of this problem. Okay? So here argmax here is the set of optimal strategies or best responses that maximize player I's payoff. Okay? Okay, so BRI sigma minus I can include multiple strategies. Okay, so then what is the definition of Nash equilibrium? So for any normal form game, so remember that normal form game has three ingredients: set of players, set of possible actions, and payoff functions. So for any normal form game, a strategy profile sigma prime. So strategy profile simply means collection of strategies of different players. Okay, so sigma strategy profile means just collection of player 1 strategy, player 2 strategy, blah blah blah. Okay, so we call that collection of strategies. We call that strategy profile. Okay, so strategy profile sigma prime. So it has to specify each player's strategy, sigma I star, is a Nash equilibrium if and only if player I's strategy is belonging to this best response set. Okay, so which means that to put another way, we say a strategy profile is best response if and only if all players choose best response to each other. Okay. Or equivalently, we can say sigma star is best equilibrium if and only if this inequality holds for any I and for any sigma I. Any questions about definition of Nash equilibrium? Okay, then let's try to appreciate what is really going. Let's discuss what's really going on here. So I just gave you a mathematical definition. Okay, so then let's discuss what is kind of really Nash equilibrium means. Okay, so again, here still we have some sort of rationality here, right? Because player one chooses best response, and here best means payoff maximizing. So all players choose payoff maximizing strategies. So which means it kind of presumes rationality of each player. Okay, so that's one thing here. And the other thing, which is also very important and related to our discussion at the very end of last section, before the break time. Here, sigma I star has to be best response only to sigma minus I star. Okay? So which means that player I's strategy, sigma I star, has to be best response to what the other guys actually play. Okay? And the idea behind this is something we call rational expectation over the other players' strategy. By rational, it actually means correct expectation. So rational expectation, that means correct expectation in our context. Okay? So Nash equilibrium really actually, we can interpret this Nash equilibrium with, okay, so here we assume two things, the common knowledge of rationality and rational expectation of opponent strategies. So the second part here, rational expectation, means all players have the correct expectations about others' strategies. The strategy they will actually play. Okay, so they have correct expectation. So they know that somehow they know, all players know, player I knows, for example, the other players will play sigma I star. They have correct expectation. Moreover, with that correct expectation, of course, they have to choose best response to that expectation. Okay, so that's Nash equilibrium. Rationality and rational expectation, or correct expectation. Questions? Okay, so Nash equilibrium assumes two things: common knowledge of rationality and common knowledge of correct expectation. Okay, so it assumes more than the previous one, strictly dominated strategy, elimination of strictly dominated strategy. So using Nash equilibrium, you can make more specific, more narrowed prediction about the game's outcome. Okay? The set of Nash equilibrium has to be smaller than the set of outcomes that survive the process of iterative deletion of strictly dominated strategies. It has two long names. So anyway, you see my point, right? So Nash equilibrium assumes more than what we assumed previously. So the set of Nash equilibrium outcome has to be smaller than what we got before. Okay? Okay, so another thing here is, okay, so this is also kind of something I have to emphasize. So here, another way to define Nash equilibrium is, okay, so the strategy profile is Nash equilibrium if and only if no one has profitable deviation. By profitable deviation means some deviation that provides a higher payoff than the Nash equilibrium strategy. Okay, so here all players has they has no way to increase their payoff, right? By choosing other strategies. So sometimes we say in this situation we say that no players has profitable deviation. What is important here, what I like to emphasize here is, okay, so here we only consider unilateral deviation. By unilateral deviation, what I mean is, deviation by only one player. So, okay, we don't really, think about the situation. What if player 1 and player 2 deviate together at the same time? We don't really think about, consider that kind of deviation. So here, we only check whether there is unilateral deviation. If there is any player who can divide, independently, unilaterally, and check whether he has or she has that kind of unilateral deviation. Okay? So that is related to our very first assumption actually. Remember that we also assumed that all players choose, in normal form games, all players choose their actions and strategies independently. Okay? So as long as that assumption, independence assumption is valid, we're gonna focus on Nash equilibrium. We're gonna only check whether there is profitable unilateral deviation. Of course, depending on context, there is some cases that you have to actually check multilateral deviations as well. But in this lecture, we are going to focus on the case where all players choose their decision, make their decision independently. Okay? Okay, so concept of Nash equilibrium is kind of easy to catch, easy to understand. Mathematically, it is just any strategy profiles that satisfy certain inequalities. Okay, and philosophically, it is also not really that difficult to understand. So you can understand, interpret it with common knowledge of rationality and rational expectation. So it's kind of easy to catch conceptually at least. But sometimes, in many cases actually, if I ask you to solve for Nash equilibrium, it's not really that easy task actually. Sometimes. So I'm gonna try to give you sufficient number of examples in the lecture and also problem exam. Okay. Okay, so let's look at our previous example again. Let's revisit prisoner's dilemma. So first of all, you can easily check DD is Nash equilibrium. Actually, this is really kind of obvious because remember that DD is dominant strategies, right? So Nash equilibrium only narrow down, what is the your set of reasonable outcomes, right? So DD was the outcome, the only outcome, reasonable outcome with our previous criterion. So Nash equilibrium has to only narrow down your set of reasonable outcomes. So there is no other things you can Okay, so it is also kind of interesting to sum up. Actually, DD is actually inefficient outcome, right? CC is clearly better outcome than DD, in the sense that both CC is how Pareto dominates DFT. So DD is clearly inefficient outcome. That's another quick remark. Historically, prisoner's dilemma game considered very interesting, especially in old time, like 30s or 40s, because back then in 40s, people, especially economic theorists, still they believe in the idea of invisible hand. Okay, so they believe that if we allow all economic agents to do whatever they want, the outcome should be something desirable outcome because of the something we call invisible hand, the idea of invisible hand, Adam Smith. But this game was clearly a counterexample to that idea. So here, player 1, player 2, they are allowed to choose whatever they want, but eventually they end up with a very bad outcome in the end. Okay. Okay, so as I mentioned already, solving for Nash equilibrium is sometimes difficult. So I'm gonna give you another 2 useful lemmas you can use in solving Nash equilibrium. Okay. So the first lemma says that so let's focus on finite normal form games. So finite normal form games, that means set of players is finite and set of actions, all of them are finite for all players, right? So all players have finite set of actions and number of players that is also finite. Okay? So let's focus on finite normal form game. Then sigma prime, so this is collection of all strategies, all players strategy, is Nash equilibrium if and only if this inequality is true. Okay, what does it really mean? Okay, so here left hand side you have, so sigma prime is our candidate for Nash equilibrium. So left hand side is the payoff in equilibrium. Okay, so left hand side is payoff for player I that he or she will get if all players follow the equilibrium strategy. Okay, the right hand side is the payoff that, so still all other players, they stick to the equilibrium strategy, but only player I deviates and choose AI. Okay? And still payoff is smaller than the equilibrium payoff. And that is true. Let's say that is true all AI, all pure strategies, and all player I's, then sigma star is Nash equilibrium. Okay, so this is actually really useful lemma in the sense that, so in order to show that a sigma star strategy profile sigma star is Nash equilibrium, we have to show that all players have no profitable deviation. Okay? And when you say deviation, that includes all mixed strategy, right? But this lemma tells that, but still this lemma shows that actually you don't really have to check whether all these strategies are profitable or not. What you only have to do is you only have to check whether there is profitable deviation in pure strategy or not. And as long as there is no profitable pure strategy, as long as if there is no profitable deviation in pure strategy, then our candidate of Nash equilibrium is really Nash equilibrium. Okay? So it is really useful lemma in the sense that, again, it reduces the number of inequalities we have to check. Without this, basically we have to check infinitely many inequalities because there is infinitely many possible deviations for each player, right? But using this lemma, you only have to check finite number of inequalities. You only have to check whether there is any profitable deviation in pure strength, and that's it. So in that sense, this lemma is super useful. And proof is kind of actually easy. Actually, this is proof for this lemma is kind of very similar to the proof of our previous lemma for strategic dominance. Okay, so first of all, let's say, so this is again if and only if statement, so you have to check both directions. First of all, let's say this is Nash equilibrium, sigma star is Nash equilibrium, then it is clear by definition of Nash equilibrium, if this is Nash equilibrium, we have to have that there is no pure strategy, there is no profitable deviation in pure strategy. Okay? So one direction is trivial, okay? So what is more interesting is the other direction. Let's say there is no profitable deviation in pure strategy. Then from that, we have to show that there is no profitable deviation in mixed strategies. Okay? So that's kind of easy. You can prove this way. So let's say this is true for all AI. So basically it says that there is no profitable deviation in pure strategy. Then for any sigma I, you can show that this is weakly better than this because, okay, so if you calculate this term, this is equal to this summation. So this is exactly what we did for the lemma proof of our very first lemma at the beginning of today's lecture. Then once you write down this way, you can see, because of this inequality, this thing is larger than any term, any UI term here, right hand side. Okay? And right hand side is simply average of these UI terms. And all of them are smaller than left hand side. So average has to be also smaller than the left hand side. Okay? So that shows that actually even if you have checked, if you give me any arbitrary mixed strategies, this one, equilibrium payoff is weakly larger than payoff deviation. Okay? So this proof is really simple. It's kind of almost obvious after once you actually write down expected payoff in this form. Once you could write down, this, once you see that this expected payoff is actually equal to this one, then the proof is kind of obvious. So remember, we assumed here for finite normal form game, we assume normal form game we are considering is finite, but you can also prove a similar result for infinite games as well. So basically, you have same result even if you allow action spaces are infinite. Okay. Okay. The second lemma is, let's say G is again finite normal form game, and let's say, okay, then sigma star is a Nash equilibrium of G if and only if for every player I, every pure strategy in the support of sigma I star is the best response to sigma I star. Okay? So what does it mean? Let's say you have another candidate of Nash equilibrium, and in that Nash equilibrium, player I randomizes, for example, two actions, A and B. Okay? Then that mixed strategies has to be best response to the other guy's player, right? So that's the definition of Nash equilibrium. But in order to check, so and that is true. The statement that sigma I is best response to the other guy's player. That statement is true if and only if two actions in the support A and B, if both of them are best response, then sigma I is also best response. Okay. So again, the proof is kind of similar, very similar. So we would like to show that this is equilibrium, sigma I star and sigma minus I star. So again, you can write this payoff in this way. So with probability here, sigma I star AI1. So this is the first action that player 1 can choose. The payoff of player I is this one, right? With probability this, player I will choose AI1, and the other guys will place these strategies. So that is the payoff in that case, and that is the case with this probability. Okay? And the other possibility is player I chooses the second action here, and that happens with this probability. And in that case, payoff is equal to this. And that has to be this payoff has to be the larger payoff, larger than the case where player 1 chooses this action with this probability. Okay? So here, left hand side and right hand side, the only difference is that on the right hand side, player I chooses action 1 with this probability and action 2 with probability 0. Okay, so that is one of possible deviations, and that payoff has to be lower than equilibrium payoff. So we have to have this inequality. And then you can see this term and this term are cancelled, and you can see this implies this inequality. Okay, so I'm going here a little bit fast, but I just want to leave it kind of as your practice or exercise, but I just try to sketch what is the idea here. Okay, so from this you can get this inequality, and switching the role of these two actions, then you can get the reverse inequality as well. So you have two directions of inequalities, then they have to be the same. Okay. Okay, so this lemma is actually really useful lemma. So let me illustrate this a little bit more, slightly different way. Okay, so think about the game of the rock, scissors, and papers. Okay, so here you will see actually what is your play. Let's say you have to play rock, scissors, and papers right now. Then what is your strategy? What strategy will you play? I believe most of you play just randomized 3 actions, right, with equal probability. And that is actually, you will see, I'm going to show you that actually that is Nash equilibrium. Okay, this is actually Nash equilibrium. Then both players choose rock, scissors, and papers with equal probability. They just totally randomize 3 actions. Then think about how you could justify your randomization. Typically you can justify your randomization by saying that there is no really difference between rock, scissors, and papers, right? If you choose rock, if you choose scissors or papers, the probability that you can win is exactly the same, right? So that's typically the way you justify your randomization. And that's actually the right way to justify your randomization. Let's say winning probability is higher if you play rock rather than scissors, then clearly randomization is not your best response. You have to choose rock with probability 1, right? The way you can justify all 3, randomization of all 3 actions, the way you justify their randomization is, that randomization is justifiable only if